All right, let's talk about best fit lines and prediction. So it's important to note that data rarely fits a perfect line, right? This would be even r equals 1 or r equals -1, right? That's our correlation coefficient. So we want to, for the scatter plot, we want to find the line that has the best fit. And we call this the line of best fit, or the least squares line. Okay, the process of finding this line is called linear regression. Now we are not going to calculate these, but I want us to know how to interpret them and how to find them. So the best fit line on a scatter diagram is the line that lies closer to the data points than any other possible line, okay, according to a statistical measure of closeness, which we aren't going to get into, but it's the line that's closest to all the data points. So when we have a best fit line, we can make predictions with this best fit line. So here we have the weight of animals and their age. So what is the weight of an animal that's 15 years old? So I would go to where age is 15, and I would say, oh, at 15 years old, it weighs 15 pounds. Okay? What's the weight of an animal? Sorry, what's the age of an animal that weighs 20 pounds? So I go to 20 pounds. I go over to my best fit line, and I would predict that it would also weigh, it would be 20 years old for 20 pounds. Okay? So we can use best fit lines to make predictions, but we need to be careful when we do that. So here's some cautions. 1, if the sample points lie very close to the best fit line, the correlation is strong and your prediction is more accurate, right? If you have a weak correlation, you do not want to use that line to make predictions, okay? It'll be really less accurate. Don't use a best fit line to make predictions about the bounds of the data points to which the line was fit. So in the previous slide, right, we were guessing the weight. We were comparing the age of an animal to its weight. I don't know what animal. Maybe like an emu. No, probably not. But we were doing that, right? And if I went and you saw, oh gosh, guys. Okay, here we are, right? And what if I said, okay, what's the weight of an animal that's 50 years old? First off, not a ton of animals live to 50 years old. We couldn't predict past our graph. We couldn't predict that, oh yeah, I'd weigh 50 pounds, right? So you always want to make sure you are not making predictions beyond your data points, right? We cannot use this data to tell the future. Okay, so also the best fit line is based on past data, right? Oh, I just said this, right? And it might not necessarily result in valid predictions of the future, so we can't predict the future. Don't make predictions about a population that is different from the population from which the sample were drawn. So if we were studying the weight and age of emus, we wouldn't want to do this to use the same data set to compare the weight and age of ostriches, although they look really similar, not the same population. I'm just really glad I got to talk about emus in a statistics video. Okay, and last but not least, remember that a best fit line is meaningless when there is no significant correlation or the relationship is nonlinear. So by significant correlation, we mean weak. It's meaningless if there's weak correlation. So let's state whether the predictions should be trusted in each of the following cases and why or why not. So, you found the best fit line for the correlation between the number of hours per day that people exercise and the number of calories they consume each day. And I've used this correlation to predict that a person who exercises 18 hours per day would consume 15,000 calories per day. What's the problem with this? First off, nobody is exercising 18 hours a day, right? That gives you like 6 hours to sleep. Also, if you were exercising 8 hours a day and you needed to eat all these calories, I don't think you could do that in 6 hours, okay? So, people don't exercise 18 hours a day. You cannot predict past the bounds of your data set. Next, there's a well-known but weak correlation between SAT scores and college grades. You use this correlation to predict the college, to predict the college grades of your best friend from her SAT scores. She's great. She's a good best friend. The problem is you do not want to use this correlation because it is weak, right? It's not a true, if there was a strong correlation, we could totally do this, but because there's a weak correlation, we're not going to. Next, historical data have shown a strong negative correlation between national birth rates and affluence. So countries with greater affluence tend to have lower birth rates. This data predicts a high birth rate in Russia. What's the problem with this? The problem is this uses historical data, right? This is historical data, okay? This is not the current data, so we do not want to use this to predict. So, best fit lines in R squared. So the square of our correlation coefficient is the proportion of the variation in a variable that is accounted for by the best fit line. So R squared is the proportion of variation, and it tells us what proportion of our variable is accounted for by the best fit line. So let's say I have a correlation coefficient of 0.5. That's like a weak correlation, right? If I take R squared, that gives me 0.25. So 25% of the variation in the data is accounted for by the best fit line, right? So that makes sense that it's a weak correlation if only 25% of the data is accounted for by the best fit line, right? This is why you want strong correlation. If I had R equals 0.9, R squared would equal 0.81, so that means that 81% of my data would be accounted for by the best fit line. So in this first example, the proportion of variation is 0.25, so 75% of the variation in the data must be due to other factors. In this case, only 19% of the data of the variation in the data is due to other factors. So let's take a look at this. Political scientists are interested in knowing what factors affect voter turnout in elections. So one such factor is unemployment rate, okay? So we've collected data for every presidential election year since 1964, and it shows a very weak negative correlation, so we'd have like a line kind of like this, right, between unemployment and voter turnout. So should we use the unemployment rate to predict voter turnout in the next election? No, right? This is a weak correlation, okay? If I take my R squared, which is 0.1 squared, negative 0.1 squared, which would give me 0.01, right? This means that 99% of the variation is due to other factors, not unemployment. Okay, so something to think about are what are the other factors that could influence voter turnout? It could be relatability of the candidate. It could be, is the weather really bad? Do you go vote in the snow? I go vote in the snow. But some things like that. So it's important to keep an eye on what other factors can affect voter turnout.